Hello, everybody. Welcome to today's current seminar. Today we have two speakers, two talks. Our first speaker is Jie Zhao. He will be giving a talk on resolve abnormal convergence issue in deep operator network. Zhao is a researcher at Pengcheng Laboratory, China. He received a PhD degrees in theoretical physics from the Institute of Theoretical Physics, China Academy of Science in 2014. He subsequently conducted postdoctoral research in the Department of Physics, University of Zagreb, Croatia. Since 2017, he has held research positions at the China Academy of Engineering Physics and Pengcheng Laboratory. His research interests include theoretical nuclear physics and the development of computational and simulation methods for quantum many-body problems, with a particular emphasis on applications of artificial intelligence. With that short introduction, the floor is yours and you can start your presentation.
Yeah, okay. So first, thanks for this good introduction, and also thank the organizers to invite me to present our most recent research on this works. As so let's start. So for our talk, many include this four parts. First is the introduction and motivation, most from the point of view of physics, and the second point is a simple introduction about the DeepONet and the related abnormal convergence in CO. And the third part is about our improved DeepONet and the related results and discussions, and finally, a very simple future perspective. Yeah, and first come to the actually, this is a most point from my background. So it's the first question is how to model the real world. Actually, from the very different scales, but it can all described by an operator. So next, I will introduce several examples at different length scale. The first one is the fluid flow. I think this most people is more familiar about these topics. No matter for a very simple flow and a very complicated tabulated flow, it can be described by this famous NS equation. In these equations, there are several kinds of physical quantities like velocities, pressure, temperature, and viscosity, and etc. They are all included in these equations. We can do the simulation or solve these equations and to get some result. And with this result, we can approximate the phenomena from the real world. And now let's come to another example. This one is from the optical communication. This is something I'm working recently. And in this system, there was a very important circuit. The function of this circuit is transform the electrical signal to light, or transform the signal of light to electrical. And look closely into here, there was this kind of structure. It's the light coming this way, and here, this is the electric signal come in this way. And with this very small structures, it can transform the electric signal to the light signal. And look close to the a critical component. It look like this. So actually, the electric signal is operated in these two ends, and how it controls this signal, because at different when the electric signal comes, and the density of the electrons and holes can vary, and then it can change the refractive index, and then they will get the transform the electric signal to light. And so how to describe this kind of phenomenon actually is described by this kind of 3 or 4 coupled equations, include Poisson equations, and these equations to describe the drift and diffusion of the electrons and holes. This kind of structures usually have the length scale of nanometers, 10 nanometers or 100 nanometers. Actually, is compared to this kind of length scale is very much small. And here comes another example. This one is actually many worked on is about nucleus. For the size of this nucleus is about Fermi, so it's about 10.15 meters. It's very, very small, but we still can describe this system via different kind of equations. So if we look at the nucleus as a whole and to describe its collective motion like rotation or vibration, it's usually described by this kind of Schrödinger equation. So if we look at a little bit deeper and take electrons, take each nucleus as a wave function, then it can be described by the density functional series. Although this series start from the quantum field theory, but finally we arrive at this kind of coupled Dirac equations. And so now the task becomes the solve of this kind of coupled equations. And actually, we can look at a little even deeper and treat each nucleus as an individual point particle. And in this case, we have to describe this system as a kind of many body quantum many body equations and to solve this equation exactly. So from these examples, we can see although these systems have very, very different length scale from the macroscopic one, which is described by the classical physics, or the motion is covered by the Newton equation, or to the macroscopic systems like electrons, nucleons, or nucleons, which is covered by the quantum physics, which is can be described by Schrödinger equation and even quantum field theory. All of these systems vary from the point of mathematics or from the point of the physics, it comes to various linear or nonlinear equations. This kind of equations have very, very different form, but take this one for example. The Hamiltonian itself is an operator, and the formal solution to this one is also an operator. So the task is now comes to solve these equations or find the corresponding operators. And then how to solve this equation or how to find these operators. And traditionally, there are several methods that are usually adopted. So in the coordinate space or in some fields called zero space, it can be solved by finite difference method, finite element method, or finite volume method. It's more or less similar. And take this one as an example for the finite element method. We first discretize the region we are concerned to small triangles or subregions, and in each kind of in each triangles we describe these variables as expand it on some base, and finally led to some matrix equations. And another method is the base expansion. This kind of method is usually used in solve the quantum many body problems or quantum physics. So first we set or choose some kind of complete set of solution of some operators as a base, and expand the variables in this kind of base set, so it can be expressed in this form, and in this way the equations or the operators will come to the matrix, and still we come to solve all these matrix equations, and finally we can get the result. So in this way, many of the efforts are developed to find a good base set. This is very important because if we can find a good base set, they finally lead to a smaller matrix, and then it indicate a less memory and a faster solving speed and a high accuracy of this result. But for different equations, and even for same equation but with different situation, the good base or the optimal base is different. So this is how to get a good base is really a problem, and this is also what we are really concerned. And another kind of method is the AI-based method, which is developed very fast in the recent years. And for this method, I think all of you are experts of this one. One is to learn the solution function directly. For the data driven, it can start from the data from the experiment or from the simulation, or we can incorporate the equation itself to the rules, and or combine these two informations, and then to train a network to represent the solution function as a neural network. And another popular method is to learn the operator itself. For example, the famous Fourier operator, neural operator, or DeepONet, which is a topic we are concerned in this presentation. So since we are learn of operators, so the input of the operator is a function, and the output is a ladder function. So the DeepONet is composed of these two branches and subnetwork. One is called the branchlet, and the other is the trunklet. And the branchlet is take the sample of the function, and the trunklet is take the values of the spatial coordinate. And because this one is exactly have the same form of this universal approximation theorem for operators. So the theorem governs it can have a good approximations, but still we don't have the exact numbers how to choose this kind of hyperparameters. Now let's have a close look at this the form of this theorem. Actually, if we take this part together, so it can take this is exactly the one to described by the branchlet, and this one is described by the trunklet. So actually, the branchlet gives the expansion coefficient, and the trunklet gives the give the expressions of the base set. So this have the exact form of the we are used in the base set method to solve these equations, or to solve quantum many-body systems. So from my point of view, I'm really interested about these questions. Can we use DeepONet to learn an optimal base set that's better than handcraft one? This is also the start point I involved in this work. And to have a base set, we must have one key point is one should have a good convergence properties. Because in the base expansion method, the base is usually have infinite dimension. We must have some truncations. And to ensure that we have enough truncations, we usually will have to vary or increase the number of the base and to check whether we get converged with that. So fortunately, from this paper, they prove they got that lower bounds of the DeepONet. They in this paper they state that for if we restrict to the linear subspace of dimension p, then they have a lower bounds described by the eigenvalues of this some operators related to this one. This means that although it's not necessarily guaranteed we can arrive at the lower bound, but we can try our best to design or DeepONet or both subnet works and to approach these lower bounds. And in this way, from this expression, we can say that so if as the base dimension increase, the lower bound could decrease, and this is what we want to real applications. So the first task it comes to me is we have to check whether the original DeepONet is already good enough to describe this kind of problems, or to check whether as the hyperparameter p or the layer width of the both subnetwork increase, the error will decrease a lot. So let's use three typical examples. Most are used in various papers about the AI-based method. The black one and the red line shows the results from the from different attach or remove activation function. For the first one, you see with these two activation function, one is increase and then decrease a little bit, and another one is decrease. This one seems nice, but this one is certainly not. For the second problem, the situation is very different. With the attach activation function as the layer width or p increase, this one increase a lot, and but instead for the remove with activation function, it increase and first decrease. And for the third example, with the remove activation function, it seems almost changes, but for the attach activation function, it then increase and decrease. So from this result, it says that as the layer width or the base dimension increase, so it seems we cannot have a definite trend how it changes. It can increase or can decrease, and actually we don't have any definite conclusion. So this means at least from the point of their application, the original DeepONet is still not well enough. So we want to ask question why this happens. Why and does it possible to improve this a little bit? So let's closely look at these expressions and the corresponding output from the neural network. What we are really concerned at this stage is the base set or the learned base functions, actually the output from the truncated can be viewed as some discrete variable representation of the learned base functions. This method is also mostly used frequently used in quantum physics to solve these equations. So from this point of view, so each column of this the output from the truncated is a discrete representation of each base function. Each base function. In that case, we can analyze the property of these base functions while analyze the property of the truncated matrix. So we first perform an SVD analysis of this matrix. From this we can analyze what is the relations of the space functions. In each column, it is for one example, but it has a very common trend. So as the smaller, so in any case, the eigenvalues for this truncated matrix decrease very fast. And so if we take some values as truncation errors and sort below some point, and take the sort it as the zero eigenvalues, we can see that as the when, for example, here we take 10 minus 5, and so when the base set or base dimension is small, so it's more or less fine. But as we increase the weights or the weights of this base set, and you see these eigenvalues will decrease very fast, trend to zero. This simply indicates that this node base function is highly linear dependent or approximately linear dependent. So this indicates that although we increased the weights or we try to include more base, but the finally learned base functions are linear dependent and led to the effective dimension of this base set expand by this base set is much smaller than what we want. So from this point, it could explain why the errors is not decrease as the layer width for this increase. The error is not simply decrease. It can vary in very different ways. So they come to the questions. Since this limit the applications to real problem, how to fix it, we can borrow ideas from our experience and solve the real problem from the base set method. In our base set method, in most cases, we choose a circular base set and ensure this base are linearly independent. So from this point of view, we can do some additional operations to make sure the finally output from the truncated is linear independent and circular. So start from this idea. So we first set the diagonal element from the original truncated to 1 and to disregard the upper part of these values, or set to 0 of the upper part of this matrix, and then we finally do an QR operator and let only keep the Q matrix as the output from the truncated. So the first operation ensures that the space set are linearly independent, and the QR operation ensures the finally obtained base is orthogonal. So this modification is very simple, so that it really works. So to check whether it really works, we still play it on the 3 examples. And the black one is the results from the original one that we have already shown, and the red one is the result obtained from after our modification. We can clearly see that in this case, in most examples, no matter we use activation function or TensionNet or ReLU, it can have a good convergent result. That means if we increase base deformations, the errors will decrease monotonically, except for these examples here. At the last point, they increased a little bit. And at this point, I still don't know why this happens. And additionally, all of the errors obtained when at large layer weights or large base deformation, base dimensions, the errors is much smaller than the original one. So to check whether it really works, so I plotted one. Actually, here I only showed one randomly chosen examples from the data set, and this shows the result compared from the exact one and predicted from the original DeepONet and our modified one. We can easily see improvement from the absolute error. Our improved one is much smaller than the original one, which is consistent with the results from the previous slide. So here is from this the one of the bigger equation. This is a one-dimensional case. We can see more clearly the improvement even from the comparison from the exact values and our predictions. We can see so both from the errors and from this results, their comparison, the improvement is significant. And here is the fellow example shown in this paper, and for the third problem, still we can see the improvement directly from the absolute errors. And here is the fellow shows another example for the 3D, because in these two cases shown in this original paper, we only have one-dimensional and two-dimensional results. Here is a simple result of the three-dimensional identity operator. We can see that when increase the layer weights, the original DeepONet will increase a lot. The errors will increase a lot, but for the our modified one, it decrease. Since in our modification we have some additional operations, certainly it will have both as a training and infer stage, it will cost more time. But and how is the time increase? This is most concern. Actually, we from our examples or it seems so in all of the ratio of the time cost during training stage compared to the original one is only increased less than 30%, so it's still acceptable. This is because in most cases, the base set cannot be too huge. In that case, the computation is not so time consuming. So this comes my end of this talk. And From the previous result, we show that our strategy is still not perfect. And so I believe there must be an even better strategy to overcome these problems. And this should, I believe they must have, but of course, still I didn't find them. And another one I'm mostly concerned is that we hope we can use this method to obtain the better base set than our usually previous used the handcrafted one when used to solve this quantum many body problem. So this is all my talks. Thank you.
Thank you so much. So now we open the floor for questions. Do we have any questions for the speaker?
I have
Yes,
a question.
Youngkyu.
Yeah, I'm Youngkyu from Brown. I'm postdoc working with George. I'm just have a simple question. When you train your network, the QR DeepONet, during the training phase, you have to do QR decomposition, or after train the network, you can just apply the QR decomposition and just pick the Q.
In my case, I only simply include this QR decomposition at every stage during the training because I sure from the time it's not increased too much, so I include at every stage. And I didn't check whether we can after several training stage and include it. I'm not sure whether it works. It could be.
Thank you.
Kamal.
Hi, I'm Kamal from Brown, working with Professor Kandialakis. I have a question on slide number 12.
Number 12. Yes.
I think I miss how the triangulation, what is the operation done after the trunk, before the QR?
Sorry.
After the trunk and before the QR, how this matrix is obtained, like the upper triangular matrix?
So it included in here, we can actually, I think you can see this number, right? So first we have the output from the trunklet, and then we set the upper part of this one to 0. And then for the diagonal element, we set it to 1. So this stage will ensure all of this so this one is our full rank. This will ensures the linear independent. And after this one, we make a QR decomposition of this matrix. And then
it's just
keep the
removing
Q.
removing the top portion and replacing with 0, or like any operation is there?
Operation
Like any matrix operation.
Matrix what? Sorry, I didn't got your point.
So after the trunk, the zeros are only like there is no calculation for A1, 2. These all are same.
A1, 2. Which kind of A1, 2? Oh, I didn't make any calculations of A1, A2, A11 or A22. It's the original value from the trunklet.
Okay, so only the upper half is replaced with 0. Okay, understood. Thank you.
Yeah.
Because it was
yeah.
not, I read your paper, it was not there in the paper also, I think.
Youngchon Shin is here, who wrote a similar paper but in 2 stages. Youngchon, you have any questions?
Hi.
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 This is Yan Jong. I'm not sure whether you're aware of a paper of mine, the two-step DeepONet paper.
Yes, sure.
How it is different from two-step training and yours?
So first, in our training state, we don't need to separate it to two states. We can train it as usual. And the most different part, I think, is this part. Although you still have the QRT computation or something, here I include this kind of operation. Actually, this part is very crucial since it can ensure this matrix is a full rank and finally got the linear independent base set. And also, I have to do some comparisons about the your two-stage method and our case. And in some case, our result is better than yours.
Okay, I don't clearly see significant difference between this one and the two-step. So that's why I was asking. And
Yeah.
your paper
Yeah, I
doesn't
think that's
really elaborate the difference between our method and yours, just a little remark at the end of the conclusion. So I wasn't that clear if I understand your method is significantly different from what I have done. So it
yeah, I
would be
think I
great if
have
you can a
some.
little bit elaborate the big difference between that one and yours.
Yeah, I think I have a few sentences to comment on this point in the paper.
Yeah, that's all I'm asking. Just I couldn't really see the big difference between mine and yours. That's it.
Yeah, yeah, I think the critical point is this one at this operation is very crucial. So without this one, it doesn't do not have this kind of how to say, this kind of effect.
It seems to me it's the equivalent operation. So
no. So if without this operation, even if we can do this one, but still we cannot guarantee this kind of linear independent.
John, I think the question here is how different are either of the methods from a POD basis?
With what?
With a PCA, if you do PCA in the outputs and you get a basis,
Yes.
because I've done that with a two-step method, and in some cases we didn't see big difference. I mean, maybe the 128th mode. And there are cases that you can make that you can show that it's different, but I think a three-way comparison here is warranted. That is, this method, let's say one-step method versus two-step method versus POD. Maybe you can convince Yankyu, your compatriot, Yankyu Lee, to do this, since he needs it for preconditioning the hints method.
Yes, you're right.
Yankyu, you want to do it?
Yeah, we should
Yes,
have more
I'm
comparison.
actually interested in that, the QR DeepONet. I don't know why. Actually, I also try to use the two-step DeepONet for the very difficult geometry, and I'm just curious that is there any difference between that Q and the Q from two-step DeepONet?
Yeah. And different from POD, because we know the POD work for the precondition, right? So
yes.
So the discussion we had earlier, yeah. John, since you mentioned this two-step method, the two-step method takes, for some reason, longer number of iterations, which I don't understand why, because now you have it's like a simpler optimization. Why it takes longer if it's a single step? Raj, maybe you have experience from that, right?
Yeah, means for some cases where geometry is not trivial. So in that case, it took me a little bit time because the collocation point changes over the geometry. So that was the finding. But here in this method, the one Jie presented, there's one issue is that QR, he's back propagating through QR, and it's going to be very expensive.
Well, he said 20% or 30% more expensive.
I think the dimensionality depends on the dimensionality of the input of the trunk net. So that's really going to be bottleneck. That's the reason why Dr. Shin's paper has separated it out, because he doesn't do the QR during the back propagation. He just does the QR after the trunk is trained. So that saves a lot of cost, because I have tested one with QR being the back through back propagation, and it was like 200%, 300% higher cost for real problem, the one we dealt with the ARL. So I think that could be a bottleneck. So.
And regarding complex geometry, George, I think there's some workaround that you can address those points in a certain way that sort of like that your complex geometry being transformed into the same geometry to some extent, so that matches the good shape of the basis, but effectively turning to fit complex geometry, then that's sort of like saved a lot of computational cost in applying two-step.
You mean with masking? I think Yanqiu is doing that, right? Right, Yanqiu? You are referring to
I try to use masking, but because in the real world geometry there's a highly non-convex parts, and also actually the shape is the elements in actually the meshes are not shaped regular. That's the big problem. So if we just make a mask for that geometry, then sometimes it cannot represent the correct shape.
I'm not talking about masking strategy, but I think we can talk a little bit offline, Youngkyu, if you're interested in.
Yeah, sure.
Okay, yeah, sure.
When he's talking about the real world geometries, he doesn't mean another academic geometry. He means geometries from ANSYS, like helmets and gas turbines and cranes and things like that. Real geometries.
But you do have some mesh being created from CAD or finite element, right?
Yeah.
Yes.
Yeah, I think that then I think should be okay.
Good. Okay, keep that for your next paper then with Yanqiu. Now, Zanin, back to you.
Okay, thank you so much. Do we have any other questions, comments for the first speaker?
I have a very trivial question.
Can you introduce yourself first?
Hi, my name is Aditi. I'm a PhD student working with Professor Karniadakis. My question is with respect to the paper by Lanthaler that you presented earlier, I think in one of the slides.
So which slide?
When you introduced the lower error bound, the lower bound on the error.
The lower bound. Yes.
Right. So
this one, right? Oh, sorry.
Right. Sorry, it was the other one. The one after this.
Lower bound. This one,
Right.
Yes, right.
So here my question is right. So here my question is script by the L2 norm? Or is it any arbitrary norm? Yeah.
This one is L2. Yes.
So script y is the L2 norm, and I'm presuming your domain is bounded Lipschitz.
Yeah.
Right. I see. Okay.
Yeah.
Okay. Thank you.
Thank you so much. Do we have any questions? I don't think so. So we will close our first session a little bit early, and I think our second speaker is here. Thank you so much, Zhao, for your presentation, and we will move to our second speaker.
Yeah, okay. I will stop here,
yeah.
right?
Yeah, Sébastien, can you hear me?
Yes, I can. Can you hear me?
Yeah. Yes, thank you
Okay,
so much.
perfect.
Can you share your screen?
Yes.
Thank you for joining us a little bit early.
Yeah, no problem.
Yeah, thank you so much. Okay. Our second speaker is Sébastien Thévenin. He will be giving a talk on contribution of machine learning to the modeling of turbulent mixing. Thévenin is a postdoctoral researcher at Lawrence Livermore National Laboratory, specializing in machine learning for physics and currently focusing his research on the generative modeling of fluid flows. He received a master's in mechanical and energy engineering from Grenoble Institute of Technology in 2021 and a PhD in fluid mechanics from University Paris Saclay in November 2024, which he prepared at CEA in Paris, France. With that short introduction, the floor is yours and you can start your presentation.
Thank you very much for the introduction, and thank you to the organizers and George and Juan in particular for inviting me to this seminar. It's a pleasure to share my research with the Crunch group and beyond. So yes, today I will present the work I did during my PhD, which I defended last November 2024. It was supervised by Benoît-Joseph Gréa and Gilles Clut at CEA, and I worked with a lot of collaborators, but I wanted to highlight a few here: Antoine Briard, Balou Nadiga, and Nicolas Valade. So my research focused about using machine learning for physics, and it revolves mostly around three different topics. So the first one is turbulent mixing. So it's a very challenging problem, as you all probably know, because it's highly dimensional. There are transient dynamics, and it's pretty chaotic. We are also interested in this for a couple of reasons. Because there is still like not a full understanding, full complete understanding of these flows. And also it has like a lot of applications that we are interested in. So in this talk, I will mostly focus on the radiator instability and transition to turbulence, but I will also mention some work we've done on relaminarization of compressed turbulent plasma. A second aspect is modeling. So I create different kind of works around ODE discovery so that we can use data to identify some structural function for modeling purposes. I also carried some work about uncertainty and sensitivity analysis in order to both quantify the errors that the model does, and also try to understand what parameters or initial conditions influence the most the output we are interested in. And finally, everything is done using machine learning tools because they can help us go beyond traditional tools. So in this work, I will talk a little bit about physics-informed neural networks and CVAs. So just to motivate a little bit what we've done, so why do we study turbulent mixing at CEA and now at Livermore? So one of the applications that we are interested in is inertial confinement fusion. So in these experiments, the idea is to use very energetic lasers in order to highly compress a small spherical target so that the fusible material, which is classically deuterium tritium gas, reaches extreme temperatures and densities so that fusion reactions can occur. So you've probably heard that recently the National Ignition Facility in Livermore has reached a very impressive milestone where a target energy gain was greater than 1 for the first time. So that means that they produce more energy from the fusion reaction that they injected it in the system with the lasers. But there are still a lot of difficulties to make these high energy gains more consistently. And one of them is the development of hydrodynamic instabilities at the interfaces of this target. So the problem with that is that you could inject some denser material from the outer layer into the deuterium-tritium gas, which would cause hotspot pollution and it will reduce the target yield. So in order to design better experiments, we rely a lot on simulations, so both for design and also for diagnostics. So these simulations are multi-physics. They involve complex geometries and they are highly dimensional. So overall, they are very expensive to simulate. So that's why we need accurate but also affordable models. And these models must be able to capture the transient dynamics of these hydro instabilities. So that's what I focus on. So what's a model? A model is a simplified representation of a real system, for example, ICF or these very complex flows. Usually, you represent this system with a set of state variables. So for turbulent mixing, it can be typically the 3D velocity field and the concentration of one of the two fluids. You need some functional structures and some parameters so that you can define how these state variables will evolve in time. And you have a bunch of initial conditions and also boundary conditions that I won't talk about today. But when you have all of this, you are able to simulate a reality, right? So this set of equations is what we could call a flow order model in fluid flows because it is very high fidelity. It represents the real system really well, but it's also highly dimensional and thus very expensive, especially in turbulent flows. The number of grid points that we need to resolve all the scales of the flow evolve with as a function of the Reynolds number. So when you have like very turbulent flows, you need a lot of grid points, and so it's very computationally costly. So that's why you also need reduced order models. So for example, you could use Reynolds average Navier-Stokes models where you locally average the flow. So this greatly reduces the number of degrees of freedom that you need to solve. So again, you still have to choose a bunch of state variables for representing these turbulent quantities. You need a functional structure and some initial conditions. But you can also average this flow globally so that you represent it, like for example, the turbulent mixing layer, you can represent it with some mixing 8 expansion velocity, amount of mixing inside this mixing layer, etc., etc. So again, you have to choose some state variables, functional structure, and initial conditions. So the good thing about these reduced order models is that they have a reduced dimension, so they are affordable, including in multi-physics code, but they are lower fidelity. So the question is like, how can we use machine learning to like improve these reduced order models? So what is machine learning? So machine learning can be generally defined as algorithms that are used to enable machines to learn from data without explicit instructions. And in my thesis, I was asking this question, like, how can machine learning contribute to the modeling of turbulent mixing? So when I was writing my manuscript, I tried to organize the ideas and what I was thinking about. So I organized the different type of contribution into 3 classes of fundamental missions that machine learning can fulfill. So the first one is assistance, which globally define like the methods that will be complementary to other more traditional tools. So it can help accelerate some numerical solvers. It can provide access to automatic differentiation to provide gradients. It can also be used to augment data or other type of applications. The second one is identification. So when you want to extract information and current structures, machine learning tools are very useful. It's also in the context of the discovery of governing equations. You can identify functional structures or even variables from data. And the last one is representation. So when you want to represent, so in a very global sense, the real system based on data. So you can just want to emulate physical simulations or experiments. You can also try to make stochastic models to represent multiple outcomes or other kind of things. But overall, what we want to do in the end is to be able to use these machine learning tools together with the wealth of knowledge we already have on the flow physics. So that's what I focused on, and I know a lot of people are focusing on this in the Crunch group. So, okay, so this is the agenda for today. I will first talk about relator just to introduce you to this particular flow. Then I will show you how we built a surrogate model for the physical simulations that we did. And then it will be a bunch of applications of how we used this surrogate model to perform a number of studies. And at the end, I will present you just a couple of slides about what I'm currently working on. So let's start with the rotor instability. So the rotor instability happens when you have two fluids of different densities. Typically when you have a denser fluid on top of a lighter one in a gravity field. So as this is an unstable configuration, any perturbation of the interface between the two fluids will lead to the development of a mixing layer, which will eventually become turbulent at late times. So this transition to turbulence is very complex. It depends on the fluid parameters, but also on initial conditions. And one question I want to highlight here is that in the self-similar regime, so at very late time when it's very turbulent, we know that the mixing layer height evolves as a quadratic function of time, which can be written like this. And it has been a big debate in the relator community as to whether the self-similar growth rate alpha infinity and the virtual time origin t infinity, those depend on initial conditions or not. So I will talk about this a little bit later. So the relator flow configurations we used was 3D and incompressible, and under the Boussinesq approximation, which means that we only account for the density differences in the gravity term. So these are represented by the Navier-Stokes equations with an additional transport equation for the concentration of heavy fluid. We solved this equation later in a 3D periodic box. So yes, Boussinesq approximation means like we have like a low density contrast between the two fluids, and we used a unit Schmidt number. The initial conditions for this configuration were 0 initial velocity, so the two fluids are initially at rest, and we perturbed the interface between the two flows with this equation on the top right. So it involves a perturbation in the 2D horizontal plane, eta, and delta, which is the initial diffusion thickness. You have a little sketch on the bottom left. We further assume that this initial perturbation is a superposition of Fourier modes with random phases. And we set the amplitude so that the power spectrum looks like this on the right, so basically a rectangle. And this allows us to represent, at least in a statistical sense, these initial conditions with only 4 non-dimensional numbers. So the first one is an initial Reynolds number defined based on the linear growth rate of the relator instability and viscosity. The second one, so basically it means that when it's large, the relator instability is highly unstable and will grow very fast. Whereas when it's slow, it's mostly molecular diffusion that and viscosity that predominate. The second number is the bandwidth of the initial spectrum, so basically how many modes we have in the initial perturbation. The third one is a steepness number, so like how steep is the initial interface. So it's a ratio between the initial amplitude and the typical length scale of the perturbation. And the last one is defined similarly to the steepness number, but it depends on the initial diffusive thickness. So in this work, we were interested mostly on some global or zero-G dynamical quantities, so quantities that only evolve in time. So this correspond to global averages over the entire domain. So first, we can define some mixing size, so which is just like the size of the mixing layer, some expansion velocity. And with these two quantities, we can define a growth rate, so a transient growth rate. Then we have some vertical mass flux from the dense fluid to the lighter one. We have some turbulent kinetic energy and dissipation averages. We have a bunch of quantities that define the level of mixing that is present inside this mixing layer. So typically we have the global mixing parameter, which is between 0 and 1. When it's 0, it means that the two fluids are completely separated, whereas when it's equal to 1, they are like highly mixed inside this mixing layer. We have a dissipation for these two. And finally, we have what we call a dimensionality parameter, which represents the vertical anisotropy, so how elongated the structure are along the vertical direction. So obviously, all these quantities are related to each other through some conservation laws that you can see on the bottom left. So the first one is the conservation law for the kinetic energy, and the second one for the mixing parameter. And there are also some models that we can use that relate the growth rate of this mixing layer with the level of mixing and the anisotropy of the structures. So this will be equations that we will use to constrain our neural network surrogate that I will present in a few slides. And finally, we will work only with non-dimensional quantities. So we non-dimensionalize our quantities using the atom number, the acceleration, and viscosity. So before moving on to building our surrogate, I want to highlight that so what it means to have like these 4-dimensional numbers characterizing these initial conditions. So I said it represents our initial conditions in a statistical sense because if you have a constant value for these 4 parameters, you can have a bunch of different initial conditions, and typically this would look like this. So these are different, but they correspond to a dynamic that is similar. So what you can see on the right side is the non-dimensional evolution of these quantities, and you can see that they are basically overlapping with each other, just because we renormalized the quantities. So just to say that if we know these 4 initial conditions parameters, we are able to uniquely define the non-dimensional global quantities. This will be important for the things that I will present next. So now I will go toward surrogate modeling. So how can we make a robust surrogate? So first of all, we built a very large database of direct numerical simulations of this flow. So it's approximately 500 simulations in 1024 square by 2048 number of grid points with a very small density contrast, Schmidt number of 1, and some low viscosity. So these were simulated with the CA code called Stratospec. You have some references here if you are interested. So what we did is we sampled the 4 initial conditions parameters, RB, S, and D, inside the space. So as you can see here, this space is a bit strange. It's not a hypercube. It's because in some region, we couldn't use this initial condition just because otherwise we would have an early confinement of the large-scale structures of the flow. And also we would not resolve the small scales very well. So we avoided doing simulations in this space. So In the middle here, you can see the time evolution of all the global quantities I introduced before. And the aim will be to build a surrogate model for this physical simulation, which would enable us to extend the prediction toward like much later time, because we will be interested in some quantities that can only be computed at very late times. So we want it to be robust and provide a realistic extrapolation. So to build this surrogate model, we used a classical multi-layer perceptual neural network. So it takes as inputs the non-dimensional time and the 4 parameters characterizing the initial conditions, R, B, S, and D, which I just noted I here. And it predicts all the global quantities, like the non-dimensional quantities I introduced before, that I note Q here. So as any neural network surrogate, it is trained to minimize the distance between the predictions and the DNS data. So again, the initial conditions and time are where the simulations were performed. But in addition, we also try to impose some physical properties and constraints in order to make it more robust. So first of all, we did some transformation at the neural network output, which is made to try to impose the self-similar behavior of these global quantities. So for example, at very late time, we know that the mixing zone size evolves as a quadratic function of time. So we imposed that by the architecture itself. And in addition, we also added some soft physical constraints, so meaning some physical properties that we want to encourage. So these are typically the 2 conservation laws that I talked about before, kinetic energy and mixing parameter. And also the relation that we have between the growth rate and the mixing parameter at very late time, and a bunch of others. So this was made in order to make the neural network more robust, including when we are using the neural network in extrapolation of the simulations. So as you can see here on the left in green, for trainings like this physics constraint these physics-informed losses were evaluated also for initial conditions that are in extrapolation to the data that we have, and also at very late times that we don't have with the simulations. So in the end, we obtain a surrogate model which is both accurate and fast. So here in this figure, you have on the y-axis the prediction of the neural network, and in the x-axis the DNS values. So it kind of follows the same curve. So it's most of the time it's below 10% or even 5% error, which is good enough, and it's much faster than DNS, obviously. Typically, like the DNS we perform takes about 60,000 CPU hours on average, whereas like predicting one trajectory with the neural network takes about 4 milliseconds. So obviously, this is something very useful if we want to perform very data-hungry analysis. So we try to verify whether this neural network surrogate was good in extrapolation. So we were very limited like as to how to check this because again, it's very hard to go toward like this region of the parameter space, just because to reach it, we need to increase the resolution of the simulations, and so they become even more computationally costly. But we performed a bunch of at least one simulation here, and we compared the surrogate, and it's basically doing a good job. So that was a first check. And a second check that we did was to compare a baseline neural network, which is trained only on the data-driven loss, to a physics-informed neural network that we used. So here on the left, I will show some results from the baseline model, and on the right from the surrogate we developed. So first of all, what we can do is look at the kinetic energy conservation residual. So as you can see here, it's striking to see that the baseline neural network doesn't really fulfills this physical constraint, whereas like when we add it in the loss, obviously it becomes much better, at least in the time frame where we imposed this constraint. And another thing, we can also look at how it performs in time extrapolation. So on the left, you have the baseline model. You can see that it kind of does a crazy thing. This is not supposed to happen because we know that there are some we know how it's supposed to evolve at late times. So typically, here you have the mixing zone size and the turbulent kinetic energy. We know that this should evolve as a quadratic function of time, which is not the case with the baseline model at very late time. And same here, like a linear time dependency. So just to say that when we include all these physics informed constraints in the loss, we get much smoother and much realistically looking trajectories.
Sébastien, I have a question. So this quadratic and linear asymptotic behavior, you said that's included, right, in the loss, right? You have this asymptotic or not?
So no, it's not included in the loss. It's included in the in this T neuron here, which is like some transformations that we do. So it's like a art constraint.
Oh, I see.
So typically, just to say some details about this, we have only like a soft plus activation function, which means that if all the neurons were activated, we would have like some linear function of time for the outputs. So if we just put the neuron corresponding to like kinetic energy and mixing layer size to the square, we would expect it to learn much better like this quadratic time evolution, if that makes sense.
Yeah. So you build it in, but basically it's built in.
Yes.
The asymptotics, yeah.
Exactly, yeah. And we also have like this soft physical constraint just to try to improve it further. Yes. But so yeah, just to clarify this, on the left side, the baseline model already has this hard physical constraints. But here, what we see is that by adding this soft physical constraint inside the loss, it performs better.
Oh, I see. Even for the data-driven, you do have this built-in.
Yes. But yeah, exactly. But this is like the physical constraints which were added in the loss on the right help too for this late time growth.
Okay.
So we were happy with this surrogate. It does the job that we wanted it to do. So then we used it in a number of ways. The first way we used it was to go back to this long-standing debate in the Rhetoric community, which was whether these two parameters, which is the self-similar growth alpha infinity and virtual origin t infinity, do they depend on initial conditions or not? So because we have a surrogate model that is able to extrapolate to very late time, we can evaluate these two parameters for various initial conditions. So when we do that, we obtain these two PDF for these two parameters for a bunch of initial conditions. So there are two lessons that we learned here. The first one is that the self-similar growth rate seems to be constant because when you look at the histogram, it's very centered around one value, which is consistent with the literature, 0.020. And also because when you compare the standard deviation of this histogram to the surrogate estimated error, it's basically the same. So meaning that even if possibly this alpha infinity parameter depends on initial conditions, with our surrogate model, we are not able to see it. So this is consistent with literature. And so when you look at the T-infinity PDF, on this side, you can see that the neural network surrogate error is much smaller than the standard deviation, which says that the initial conditions are kind of retained in this T-infinity parameter, which means that even at a very late time, the self-similar growth still depends on initial conditions. So then we wanted to try to understand like how does this T-infinity parameter depend on initial conditions? So we performed a global sensitivity analysis. And what we found is that the initial Reynolds number accounts for 65% of the dependency to initial conditions, and then followed by the steepness number by 27%. So this allows us to know like which are the initial conditions parameters that influences the most the late time growth. But it was still not enough because here it's good, we can quantify this sensitivity, but we would like to understand why it depends on these parameters in particular. So the dependency on the initial Reynolds number can already be kind of guessed just by doing some very simple dimensional analysis, but it was more difficult to say why it depends so much on the steepness number. So based on these results obtained by the physics-informed neural network, we also developed with more like traditional physical phenomenology based on only like the physics of related mixing layers. We developed a very simple model which allows to connect what happens in this late time self-similar growth to the initial conditions. So this model is very simple. You can see a sketch here on the left in the dashed black lines. So it's very coarse, but it allows to connect these two alpha infinity and t infinity parameters to the initial conditions. So this, in the end, allows us to write an analytical model for t infinity based on all the initial conditions parameter. And when you compare that to the neural network surrogate predictions, it compares very well. So you can see all the small dots correspond to one initial condition estimation by the surrogate, and the dashed line is the analytical model for T infinity. So it performed very well, especially when the initial Reynolds number is very high, which is normal given the assumptions we made for building this model. But you can see that even at very low initial Reynolds number, it still gives like the general trend. So we were happy with that because we were able to explain the results of the machine learning approach with a more traditional physical approach. So now I will talk a bit about inverse modeling. So so far we have try to understand what is the influence of the initial conditions on the quantities of interest. But now, what can we do if we don't have the information about the initial conditions? So saying what we only have access to is an observation of these global quantities. So for example, here's the expansion velocity of the mixing layer and its size. We only have access to this information. And the question is, can we go back to the initial conditions based on this sole observation? So this is equivalent to solving an inverse problem where we want to estimate the posterior distribution of the initial conditions and also the time at which this observation was taken based on this observation. So with the Bayes rule, we can decompose it into several terms. So on the top left, you have the joint prior, which represents the prior knowledge we have about this four initial conditions parameter and time that would correspond to the observation. So here we made the assumption that we didn't have any knowledge of this quantities. So we just use a uniform prior. And the second term in red is the likelihood. So how likely it is to get the observation given a set of initial conditions and time. So yeah, so this is a model with a Gaussian distribution centered in the prediction of our neural network surrogate and with a covariance matrix which is diagonal and where the variances correspond to the surrogate model error. So we want to sample and approximate this posterior distribution. So we can do that with classical statistical methods like Markov chain Monte Carlo algorithms. But a problem that we anticipate is that for some observation in this phase space, we may have different dynamical trajectories that may intersect at this observation point. So that means that there might be different families of solution for this inverse problem. So this posterior distribution is likely to be multimodal. So this is usually very difficult for MCMC algorithm to do that. So I will show you like which algorithm we use that was able to solve this problem. So just to illustrate this problem, let's say you have like a very simple, your target distribution looks like this. It has like two different modes that are very distant from each other, meaning that there is two regions of high probability in your T and I parameter space. But it's very hard to go from one mode to the other because there is a low probability region in the middle. So if you use a classical MCMC algorithm like Metropolis Hastings, you might begin somewhere in this parameter space, and it will successfully go toward one high probability region. And if you perform a very long chain, you will sample from this mode very efficiently. But the problem is this mode does not correspond to the true target distribution because it has two modes. But because it has like a very low probability region in the middle, it will in practice never goes from this mode to the other. So so in order to do that, we used an MCMC algorithm which is called parallel tempering, which basically consists in adding a new artificial parameter, which is called the temperature. And basically, instead of sampling from this target distribution, we will sample from a tempered version of this distribution, which is basically the target distribution to the power of 1/T, where T is the temperature. So when the temperature is high, basically what it does is it makes this distribution much more flat, which will be much easier to go from one mode to the other with a Markov chain. So in practice, you will just run several Markov chains in parallel on these different temperature levels. And from time to time, you will propose to do a temperature swap between the two chains. And if this temperature swap is accepted, then the chain number 1 will go to the temperature level of the chain number 2 and vice versa. And you will run your Markov chain a little bit longer. And what you would usually see is that at some point, like in the very large temperature distribution, the Markov chain will be able to explore the entire parameter space. And at a later temperature swap, you will be able to go back to the target distribution, so at temperature equals to 1, and sample from the other mode. So in the end, you will be able to sample all the modes if you run it for sufficiently long. So that's what we used, and in the end, you can see here the posterior distributions that correspond to our observation. So it indeed encompasses 2 different modes, but also a third one that we didn't anticipate. And you can see on the right like the different possible trajectories that intersect at this observation point. So I want to highlight here that solving this inverse problem wouldn't be possible without this surrogate model, just because to perform this MCMC inference, you need more than 500,000 evaluations of the dynamics, and that would be obviously impossible with DNS. So now that we have an efficient way to go back to the initial conditions given an observation of the dynamical state, what we can do is use this to develop a homogeneizing strategy. Because like if we are able to identify all the possible initial conditions that can correspond to a given dynamical state, then we basically have all the information that we need to predict the future of the dynamics. So what we propose is from the current state of the dynamics, we infer all the possible initial conditions that could correspond and times that could correspond to this observation. And then we can propagate it forward in time to see like what is the future of the dynamics. So this would mean like propagating the whole posterior distribution forward in time. but we can also like choose to only forward propagate some estimates that we want. So for example, the maximum a posteriori, which correspond to the most likely trajectory. And then we can repeat that a number of times so that we can construct a whole dynamical trajectory, which also gives the uncertainty here because we have propagated the whole distribution of possibilities. So we can do that for different starting observation points, but also for different set of observed quantities. So for example, here on the left, you have only you can only observe the mixing zone size and the expansion velocity, but you could also say, okay, maybe I have access to all these global quantities, and how does that perform? So as you can see here, depending on the choice of the state vector, you will be able to predict the dynamics with more or less uncertainty. So that's something we want to take advantage of in order to try to develop a way to choose wisely which state vector we should use as for modeling. So before doing that properly, what we will do is take several observations along one trajectory just to see what the posterior distribution looks like at these different points. So here you have one trajectory, and at each star marker here, we will perform a Bayesian inference to say what are the initial conditions that are possible at this observation point. So if we do that with a complete set of observed quantities, what you can see is like when we have an observation which is taken at a very early time, we are able to identify the initial conditions and observation time very well because we have all the information that we need. But what you can see is that as the observation was taken later in time, the posterior distribution starts to spread, which means that there is some kind of partial forgetting of the initial conditions memory during the transition to turbulence, which is kind of expected. However, you can see that there is some strong correlations between the inferred initial Reynolds and observation time, which actually correspond to the virtual origin that we talked about a bit earlier. So even if there is some partial forgetting over the transition to turbulence, there is still some memory of the initial conditions that remains. When we do the same thing with a much smaller set of state variables, so for example, here just the mixing zone size and expansion velocity, you can see that even when the observation was taken at early times, we are not able to identify the true initial conditions and observation time properly. And in a lot of cases, the posterior distribution is even multimodal, which means that there are several families of solutions that are possible. So obviously, that's not a state vector that we want to use for modeling because it doesn't, it wouldn't give an accurate prediction. So based on this idea, we had to build a measure of the quality of reconstruction because we can't look at each trajectories and each observation for the entire parameter space. So what we did was, okay, so measures the quality of reconstruction. So the measure we came up with was just the Euclidean distance in the parameter space between each of the inferred samples and the ground truth that we know here just for the purpose of this analysis. And when you do that on the trajectories that I showed in the previous slide, you can see how this measure evolves with the observation time. So again, when you have access to the complete set of state variables, you have a very low reconstruction error at early times, and it grows a little bit at late times. But when you have like a very sparse set of state variables, you have not a good reconstruction. So this was only a local measure because we did it on along a single trajectory. So what we can do is do the same, but for a bunch of different trajectories and average them all. So that's what we did over like 400 MCMC inferences at random observation points. And we obtained this kind kind of curve for different sets of state variables. So Q7 is like the complete set of global quantities, and you have different choices here. And what we show is that for appropriate choices of state variables, for example, the green one here, we can have a relatively low reconstruction error, which means that these are interesting choices for building a model. So so far we have performed like resolution of these inverse problems with traditional methods like MCMC, just using our forward surrogate as a mean to evaluate the dynamics at different points. But could we also perform the resolution of this inverse problem with machine learning methods? So that's what we try to do with generative deep learning method, which is called conditional variational autoencoders. The idea is kind of similar to a classical deterministic autoencoder, except that the latent space is this time probabilistic. And what you want to do with that is, given a random draw of this latent space and some conditioning, you want to produce all the possible posterior samples of your parameters of interest. So in our context, the thing you would like to produce is samples from time and initial conditions based on some observation of some state variables. So to train this model, you have classically a reconstruction term, which means that you want to produce samples that looks like the data that you have. And there is a regularization term, which is a Kullback-Leibler divergency, which enforces the latent space to be close to a standard Gaussian. So that when you want to generate new samples, you just have to sample from a Gaussian distribution, pass it into the decoder, and you obtain your posterior samples. But in addition to that, because we have access to a forward surrogate, which allows to go from X to the conditions, we also added another term in the training loss, which is just the difference between the true conditions that we ask our model to produce compared to the one obtained with the generated samples. So in practice, we found that this helped to generate much better samples, which were more consistent with the conditions that we included. So this is a little bit of details about the training methods. I won't comment it too much, but I just want to highlight that as any multi-objective optimization task, where you have like different terms in the loss, you have to weight these different terms compared to each other. And we came up with a very simple solution, which was just based on the dimensionality of both the parameter space or output space and the dimension of the latent space. And that worked very well in practice. So in the end, we applied this to our inference problem about the initial conditions. So we start with the same observations that we used before. And on the left, you can see like all the posterior samples that we can generate with this CVIE compared to the MCMC histogram, which is in orange. So what we see is that we are able to sample from all the different modes, even if we don't have like a clear separation between the modes, and even if we are not spread as much as the MCMC. But when you look at the generated trajectories that correspond to these initial conditions and observation time, you can see that we have like very resembling trajectories. So this is quite good, and also it's very fast compared to MCMC, because with MCMC, for one observation, you would have to make hundreds of thousands of iteration in the Markov chain, and you would have to do it again for another observation. Whereas here, once the CVIE is trained, you can enter any observation and it will generate instantaneously posterior samples that correspond to this observation. So this is really fast and very useful in practice. And another thing that is great with these deep generative models is that probably you can also generalize this to like a parameter space that it is much bigger than just the 5 dimensions that I have here. So these are like more comparison between the MCMC and CVAE. And I just want to add that here you don't have like a clear separation between the modes using CVAEs, but probably using other generative approaches like score diffusion models would make even better predictions. So that's also something we are currently investigating. So now I want to switch a little bit of subject and talk about OD discovery, because so far we have used machine learning to build surrogate models that are kind of black box. So we can use them to perform analysis that will help us better understand or better model the flow of interest, but it's hard to really like understand what these models capture in the first place. So here, what we want is go back toward a more classical physicist approach, where you want to obtain a model that can be written as an equation in the end. So this is the realm of identification of nonlinear dynamics. There are a bunch of references on the top. So if we go back to like the wide definition of what's a model, you need to choose some appropriate state variables. So that was something we investigated before, how to choose wisely these state variables. And if you assume you already made this choice wisely, then you need to build functional structures. So typically, in our case, we are looking at time evolving quantities. So we want to build an ODE to represent the evolution of these quantities. So one solution that you can do is called sparse regression of or a sparse identification of nonlinear dynamics in the literature. So basically what you would do is construct a model which is a linear combination of different terms. So these different terms, you will propose different candidates. So this is a library of candidate functions. This can be polynomials of your state variables. It can be other functions, anything that you want. It can also depend on different parameters. For example, the wave number in a sinus wave. It can be a bunch of things. But what you want in the end is like, even if you propose a very diverse set of candidate functions, what you want is to be able to represent your quantities of interest with only a few terms. Because if you have a lot of terms, it's like a black box model, because you won't be able to really understand, and you will be basically overfitting your solutions anyway. So that's why you need to do a sparse regression. So one algorithm to do that was introduced, I think, by Brunton and colleagues in 2016, which is called sparse identification of nonlinear dynamics, or SIND. It's basically doing a linear regression here with some L2 regularization, but it's not necessary. And after one iteration of linear regression, you will hard threshold every coefficient of the linear regression which are below some specified threshold, which is an hyperparameter here. And you will repeat this with the remaining candidate functions, and this until convergence. So in the end, you will get a sparse set of candidate functions that represents your dynamics fairly well. Another possibility is to use sparse Bayesian learning introduced by Tipping in 2001, where the idea is kind of the same thing, but just it's in a Bayesian inference framework. So you will have a likelihood of the output variables that you want to model given the coefficients of the linear regression. And you will add some sparsifying priors so that you encourage the coefficient values to be close to 0. So we applied this method to some problem, which is modeling a compressed turbulent plasma. So this can be an application for inertial confinement fusion, where you can have a very turbulent spherical flow. And so over time, you will have an increase in temperature in ICF, And so this will make the viscosity of the fluid or plasma to increase a lot. And depending on how fast it increases, it can induce a very different, well, it can act on the turbulent state of the flow, and possibly it can lead to a very fast relaminarization. So this is something that is kind of hard to model. So if you have like kind of a slow increase in viscosity, you will just have like, this would be equivalent under change of coordinates to a phenomenology where you will first have a turbulent decline and then a viscous regime, so relaminization. So this is already well captured by some models. But when you have a very fast increase in viscosity, so meaning faster than the small eddy turnover times, then it will skip this turbulent decline and directly enter the relaminization phase. And this is so when this happens, you can show that there is a spectral imbalance in the energy spectrum equation, which is very hard to model, at least with two equations. So we based our analysis on a previous model, which was built by Perrault and Deborn-Copps, 2006, which instead of representing the turbulent kinetic energy and the dissipation of turbulent kinetic energy, it represents the turbulent kinetic energy and the integral scale of the flow. So this was based on a geometrical approximation of the energy spectrum, and you can show that when you average it to get global time evolving quantities, it looks like this. So on the right, in black, you have some results from ADQNM simulations, which were our reference or baseline solutions, and in blue you have the prediction of this PBK model. So what you can see is that when the increase in viscosity is slow enough, and you have like a classical turbulent decline, this model performs very well, at least for the turbulent kinetic energy. But when the increase in viscosity is very fast, then you have a high discrepancy here. So what we wanted to do is use this sparse regression method to try to get closer to our reference simulations. So that's what we did, and we obtained the model that you can see on the left. So it has a few more terms than the original PBK model, but the terms from this PBK model were identified too, so these were already a good baseline. And on the right, you can see the prediction of this made with this model in orange. So you can see that when the viscosity increase is very fast, you still get very nice predictions. And also it corrects the discrepancy that the model had for the integral scale. So we were satisfied with the accuracy of this model, but then we wanted to go further and try to understand why it works. So the good thing about it is because we can write it as an equation, we can try to understand what is the purpose of each term in the equation. So that's what I will comment in a second. I just want to mention first that because it's also written as an equation, you can verifies that it satisfies a number of physical properties of the flow. So for example, we showed that this model was physically realizable, which means that the turbulent kinetic energy and integral length scale will always be positive. So we could show that analytically. So this is something that is important. So when you plot the contribution of each term to the output variable for the two models, so PBK is a reference baseline model, and M2 is a model identified with sparse regression, you can see different things. First of all, the two terms of the PBK model, so one is acting in the turbulent regime, and the other is acting only on the viscous regime. That's what you see, no matter whether you have a rapid increase in viscosity or not. But with the M2 model, which is able to capture this rapid increase in viscosity much better, you can see that when the Reynolds number is very large and the increase in viscosity is slow, in the turbulent regime, it's the same term that acts and that represents the model. Whereas when the viscosity, the increase in viscosity is very fast, it's not this orange term anymore, but it's the red term. And when you have like both an increase in viscosity, which is fast, but also the turbulence acts too, you have like some kind of balance between these two terms. So basically what it says is that these two regimes can be either represented by this orange term or by this red term, or a combination of both. So if we want to highlight what is the separation line between these two regimes, we can just say that it's when these two terms are equal. So that's what we did here. And based on this, we can construct a non-dimensional number, which is a function of the viscous flow number and the Reynolds number. And when this number exceeds 122, which was based on the identified coefficients, we know that we are in one regime or the other. And when we compare that to a bunch of evaluations that we have here, it actually represents this separation very well. So what you can see is here the relative error of each model on the turbulent kinetic energy. So on the top right here, you can see that the orange and blue model, so the two models are as good. They are not, because it's when the increase in viscosity is not very fast. So both models do very well. But when we are in the lower left region, the model that we created with the OG discovery methods performs better because the relative error is smaller. We get this nice separation. Okay, so now I will just say a few words about what I'm working on. So I've started a postdoc 5 months ago at Livermore National Laboratory. And I'm currently working on trying to emulate physical simulations, but like this time the whole physical field. So here is an example of using score-based diffusion models to emulate Rayleigh Taylor simulation, 2D Rayleigh Taylor simulations. So we are making progress on this. We are able to represent very fine structures in the flow. And so this is work in progress. So this involves a very wide team, both at Livermore, but also at CEA and Los Alamos. So to conclude very quickly, I hope I showed that machine learning can increase the scope of problems that we can study. We try to organize the different applications of machine learning around like 3 general classes of contribution, which are assistance, identification, and representation. So some examples are being able to create powerful and robust surrogates, perform in-depth global sensitivity analysis, resolve inverse problems much faster than we could otherwise, and also like provide a bunch of other way to do modeling and uncertainty quantification. And to finish, I just want to say that it's always, so these tools are very powerful, but it's always very important to add all the physical knowledge that you can inside the training of these models, or at least in their use, so that you can provide new insight on the flow physics and create useful models. So with that, I just want to highlight that I did a small comics of my PhD. So you can find it on my LinkedIn page. And with that, I thank you for your attention, and I'll be happy to answer any question.
Thank you so much for your great talk. Do we have any questions? Juan.
Hi, Sebastian. First of all, thank you so much for joining us. This was a really nice presentation, and you've done a lot during your PhD.
Thank you, Juan.
Really, really good and impressive work. Maybe I just have a few questions because I may have to run for classes.
Mm-hmm.
But, in slide 16, maybe can you go back there?
Yep. Let me.
Maybe. Oh yeah, here. Here it says that you only impose the energy constraint after time 150. Right?
Before 150, yeah.
Yeah. And why was that? Why you didn't put it like?
So that's a good question. Actually, we try to impose it for longer but it mostly degraded the performance. So it's not clear why. Maybe it's because the ponderation weights between the different loss terms were not good enough or like not well balanced. This is actually something we would have to investigate to be sure. And also maybe it also compete with another term, which was the relation between the growth rate. Oh, let me go back. Yes, maybe it was also a competition with this GSS loss that we added at these very late times. So yeah, I don't have a clear answer, but I would say this could be solved by doing like better balance between the different losses in the overall loss.
So you think it was somehow like an optimization problem when you try to okay. Also, it could be like the domain becomes bigger, right? Like if here your time only goes up to 150, otherwise
Yes.
300.
Yeah, so I think what we saw is like the performance were worse, at least on the trajectories that we have. And I think, yeah, as you said, like we increase like the time span where we want our model to be good, at least for these physical properties. But you know, like when you add some physical some physics informed losses, it will compete with this data driven loss. And so technically it shouldn't make it worse because the two should be compatible. But because in an optimization framework, I would say that they will still compete with each other. And yeah, maybe that's some explanation.
Another question in this same slide with this transformation to do this hard constraint. It says like to impose the self-similar behavior. So when you say that, what do you mean? Like, do you have like an expression of how the transformation worked?
Yes, I can show you that. So, okay. So this is basically what we meant. So what I said during the talk was, so we only have like a soft plus activation function, which are just a linear activation function. So what we can think is that if all of them are activated, which is not sure, but let's say at very late time, you will have all these soft plus activations that are activated. Then basically you would have a linear function between time and the output, or a linear mapping between the two. So if you have like quantities that evolve as a quadratic function of time, you can just take this to the square, and you can hope that it will be indeed a quadratic function of time, if that makes sense. And also, like if you have like quantities that are bounded between 0 and 1, like the parameter theta here, you can just use a hyperbolic tangent on top of this soft plus, and you will be sure that it will always between 0 and 1.
Oh, okay. Yeah,
so you adjust your activation functions.
Yeah, like just the last one. So basically, yeah, that's what we do.
Yeah. So you could have adaptive activation functions that would do probably the same thing because. But anyway, yeah, that's a very good idea.
Yeah. Yeah, I mean, like adaptive activation function, I mean, it would depend, I guess, on what are your outputs. But here, because we already know what is expected growth, we can just impose it.
Yeah.
Okay. Yeah, that was a good idea. Thanks for explaining, Sébastien. Also, another question, maybe for when you were explaining about these two peaks of the distribution, you have like this this diffusive, and then when you use this tempered strategy, can you go there again?
Yes.
Yeah. First, one question here, like this temperature is like do you have some type of a schedule for the temperature? Because what usually people do, I think that like all this comes to some like physicists like this kind of trick with this temperature and
Yeah.
Yeah, but for example, they usually add like some additional constraints. For example, that this temperature has to go to 0 eventually because you want to recover the
yeah. So exactly. So the only constraint that you really have is that you need. So these are a discretized temperature. It's not a continuous one, and the only constraint that you really have is that you need at least one chain that has a temperature of 1, because it corresponds to sampling the target distribution. So that's what you want to do. But then how many temperatures you use and what is the maximum temperature used is hyperparameters. So usually well, at least what I did was to use a maximum temperature which is high enough so that I see in practice that it's flat enough so that I can explore the entire parameter space correctly, because you don't know the target distribution beforehand, so you can't really know what is the temperature you need to make it flat. But if you use like a very large temperature, then you know that it will work anyway. And the second thing is, like, I took a schedule which was in a logarithmic scale, meaning that yeah, I have like 1, 10, 100, 1,000, you know, something like this, and it worked really great in practice. But yeah, some people have worked on adaptive temperature schedules, but I didn't need it for my program, at least. And yeah.
Sebastian, there is since you're on this topic, sorry, Juan, there is a question in the chat. If you can you open the chat?
I can try.
I think it's one of your collaborators, if I'm not mistaken.
I'm not sure how to show.
It says, is there a connection between parallel tempering and diffusion models?
Yes, exactly. Yeah, so this is Benoît Joseph, my research director. So yes, indeed. I'm just trying to. Okay. Yes, so there is a direct relation between the two, because what you basically do here in parallel tempering is like you are flattening this distribution. So it would basically correspond to when you are like when the score diffusion model has like a very large level of noise, right? And so in score diffusion models so I think the direct link would more be like with simulated annealing. If you have heard of it, it's kind of the same idea with parallel tempering. You start with a very large level of noise. You explore the space at high temperature or high level of noise, and then you slowly decrease this level of noise until you get to a very small level of noise, which is impossible to differentiate from the true a sample, right? So this is exactly the same idea. Yes, you try to.
On that note, there is a talk on information theory by a postdoc from Purdue about a couple of months ago, where he made a connection like that very rigorously, actually.
Oh, okay.
So maybe it's Alex, I forgot his last name, but yeah.
Okay, I'll take a look, definitely.
Yeah.
But okay, so yeah, this is something yeah, that is very important. So it's related to my current work on score-based diffusion models. What I've seen is that if you want to reproduce like very fine structure, this fine structure kind of correspond to like multimodal distribution in the pixel space. And so you really need to have like some techniques that allows to explore the entire parameter space or pixel value space. So there are some direct connections.
Juan, are you done?
Nice. Maybe one or two more questions, if that's
sure.
Okay. Yeah. First, thank you for explaining, Sebastian. That was quite good. And in that case, in what you're doing here with this parallel tempering, you said that there were times that you would go back and forth between the true distribution and this tempered distribution, right? Like when
yes,
100. That didn't introduce any type of instability. Is that stable? Like you.
So what I meant is like, so you are running different Markov chains in each of these temperature ladders, right? So they are evolving on their own. They are completely disconnected, but from time to time, you will propose. So, you know, like a Markov chain, every time you propose a new step, and it's either accepted or rejected based on the probabilities. So the temperature swaps, you propose it, and it's the same thing. It will be either accepted or rejected based on the probability of the swap, like going from this temperature to the other. And this is the only time where there is a connection. And so yeah, I'm not sure about the instability. What you meant by this?
I think that makes sense. If there's somehow like each level should not be any.
Yeah, so basically they are completely independent, but from time to time you propose a temperature swap. They will be accepted or rejected based on the probability of going to this new space with a different temperature for both chains. And once they do that, they will evolve in this new temperature space. But what is good is like one chain typically, so it will spend time in each level of in each temperature if you run it for sufficiently long. And so this is great because when you are like in the cold temperature, so the target distribution, it's very hard to go from one mode to the other, but it can travel to a higher temperature level to then go towards the other mode, and hopefully it will do another temperature swap with a chain that is located here, and so it will go back to the temperature 1 and sample from the other mode. That's basically what it does in practice.
Yeah, so sounds good. Thank you so much, Sebastian. I think that I have a couple more.
Let somebody else ask question. Maybe
I was going to say that. Just
I think maybe some comments from about the diffusion model, maybe from Vivek, because I think what Sebastian is doing something similar to what we're doing for turbulent flows. Do you have any comments, Vivek?
Yes. So at the moment, Sebastian, are you trying? I know this is a work in progress, but are you trying to learn the evolution of a system in time with the diffusion model?
So what I'm trying to do right now is I have a set of input parameters. So typically I'm doing two things. So first thing is unconditional sampling. So basically I have a bunch of simulations at different times, different phase, different perturbation modes, and I just want to produce one possible simulation, right? So that's what happens on the left. So it's unconditional sampling. Well, here it's still conditioned on the atom number for normalizing reasons, but anyway, so it produces anything depending on the noise that you sample at the beginning, right? On the other hand, on the right hand side, what you can see is that it's conditioned, so okay, again on the atom number, but also on time and the phase. So here I ask like different output numbers, but at the same time and same phase. And that's what you can see. So it like when you have a low output number, it's kind of symmetric and it becomes asymmetric. So meaning it's not an autoregressive model here. It's really like you go from the implicit dependency, which is time, initial conditions, output number parameters, directly to the corresponding solution. But so here I just want to say on the right hand side, the dataset was only like with single mode perturbation. So there is a unique solution. So no matter really what is the sample of noise, I will always fall into this solution. So that's good. So basically it's the problem setting is deterministic. But I'm still solving it with coefficient models. And on the left-hand side, like I have a bunch of solutions every time because I'm not conditioned and there are multiple solutions. But what is great with this generative model is that you can generate all of them, right? All the solutions. So yeah, that's very interesting. Especially, for example, if you think of like maybe more applications, you could think you have control over some parameters. Some averages, something like this, but you don't control small uncertainties in these parameters. You could generate all the possible solutions and outcomes with that. And so this is one aspect, like doing robust design maybe. There is also like prediction of chaotic system like turbulence. Like if you have one current state, you can go to the next one, but this is an ill-posed problem because you only have access to the current state, right? It's not all that you need to be deterministic. So you can generate all possible outcomes. And then a third one that I will mention was doing like inverse problem as well. You have something, you want to estimate parameters. Again, you have like, multiple solutions. Technically, if you have the data set, you can generate all of them.
Sebastian, the case, I think that's the thing that we also have with Vivek is, how do you know the phase? Who will give you the phase, the correct phase?
Okay, so here it's in the dataset, right? I have the phase and I want to generate a sample with this phase. But I mean, I could just remove this from the condition and then I just don't know it, and it will generate any phase depending on what's in the dataset, right?
But yeah, that's the problem, because you will get the spectral features correctly, like we do, but then the mean error is not necessarily lower. So you're correcting the spectrum, but you're inducing phase error. Yeah.
I guess it depends on what's your real problem. Like, what do you have as information? What do you want to produce? right? If you want just to access some like average quantities or spectra or, you know, mean profiles, maybe like if you don't have the phase and the phase is not right, it's not a problem because you still have like the good statistical quantities, if that makes sense.
Well, it can affect even the mean flow. So if you have the wrong phase, it can affect the mean flow. So I don't think that's. I mean, it's not an issue.
It depends. So I would say like, so for example in ret error, like it's homogeneous and isotropic in the horizontal plane. So usually what we define as the mean flow is like the vertical profile. So it's like an average over the horizontal direction. So in this case, it's not very important, the phase. But yeah, I guess for other applications, it's very important. In that case, like either you have the information about the phase, or otherwise you just produce all possible solution and then I don't know. Yeah, that's a good question.
Yes, Sébastien, thank you. We are working on something similar. Maybe after a while, when our work becomes public, I could share your work and we could have an offline discussion.
Yeah, sure. I would love that. Same for us. Once we have more published results, we can. Yeah, that would be nice. Thanks.
Thank you. Do we have any other questions, comments for the speaker? Thank you so much. I think it's time to close the session. And thank you everybody for joining us today. Have a great weekend.
Thank you
very much.
Sébastien. Thanks for coming.
Thank you for the invitation, George.
Great talk.
Thank you.
Bye.